quantity is invariant, or conserved, if you like, in a material volume Vt, if satisfies the following conservation law. The conservation law given by dt integral. This is, imagine, is density, scalar quantity, g Vt in d3x. And if this quantity is 0, then of course, and it remains zero in time, then of course this is an invariant, is conserved. And now we can use this term to equate this part to this part. So we are saying that this quantity, if it is 0, is conserved. Okay? So this leads us to this statement here. But to have this part, so this is general law for conservation. And now I said in the introduction that we assume a fluid to be continuous everywhere, at all scales. So if it stays continuous at all scales, which is, in the past was an easy assumption. Now, as science progresses, it becomes more an issue. You know, you go to a scale where below molecular scale, how do you define a fluid at that scale? How do you define properties, physical properties at below molecular scales? Is not so easy. In the past, it was a trivial problem because they said, well, it's always continuous. Now, it's no longer such a trivial problem. Why? What has been changed? Has been changed science. Science. Discoveries. For example, quantum fluids. Bose-Einstein condensates. Quantum fluids. A vortex in a quantum fluid is a so-called thickness, so to speak, of an Armstrong. We are at so little scales that the classical concepts of fluid mechanics become very difficult to be applied straightforwardly. Anyway, if we are going down the scale as much as we want, then we can say that if this is 0, it is 0 for any elementary small volume. So, going down in scale, we may say that this conservation law leads, is not the same, but leads to the other conservation law, the differential form. So from this, we get to the differential form, going to elementary volumes, we get the differential version of that. dg dt equal minus the divergence of gu. Okay? So this is conservation law in differential form. Okay, so we have the integral form, we have the differential form. If we are allowed to perform this reduction. This is interesting. Remember the structure of this. There is a minus here, and try to look at the meaning. Leave aside the maths. You look at the meaning. It says that if this increases in time, this should decrease in space. There is a compensation of this because G is conserved. G conserved doesn't mean G constant in space and time. G conserved means that the value in time should be compensated by an opposite amount of value in space. And this is what happens very often in a number of conservation laws. So if we apply, we didn't write properly the equation for G vector. I'm going to do it now. But before I just put a sign just to show you an idea. But now we stick to the G scalar. And the G scalar applies to the conservation of mass. Is the very first equation we use in, if you like, in fluid mechanics or in physics. So we introduce a mass density, rho. This is a mass per unit volume. Of course, this rho, in general, is a function of x and t. And we have the conservation of total mass with respect to time that is written like that. And that gives us m, the mass being the integral of rho in d3x. This is density, remember. And that means that if this is true, we have the integral form that is true. So we have the integral over the volume of the derivative of rho with respect to t plus the divergence of this quantity rho u. And this integration over d3x is equal to 0. And because it is, the context is that we can go to very low scales, we can look at the differential form of this conservation law. And the differential form of this conservation law just is the equation of continuity that states conservation of mass. D rho dt better. Let me just work out here this operator that works on rho and on u. I split the two parts. I regroup the part on rho. I regroup the part on rho with the rho dt. So I have d rho dt. Remember the Lagrangian derivative, time plus space, equal minus rho div u. Okay? There is just a little bit of algebra on this equation. I skip the passages and you do the passages yourself. It's very quick. You get to this equation. This equation is the first equation in fluid mechanics or in continuum theory that is relevant. Conservation of mass. Okay? Comes from first principle of physics. Mass is conserved. From this, you go to the integral definition of mass. You apply the kinematic, not dynamics, the kinematic theorem, and you get to this equation. So this is an equation that comes from conservation laws. Now, this equation is important also from a mathematical viewpoint for many reasons, but one simple reason is that you relate the variation of rho with the divergence of u. Divergence of u. So if you assume that d rho dt is exactly 0, then it means that dvu is 0, because rho is different from 0. dvu is 0. So all the time you assume that dvu is 0, you are saying that rho is not changing Lagrangianly with time. Okay? So dvu equals 0. Solenoidal condition means d rho dt equals 0. I just point out a little aspect of language. If rho is exactly constant, is a constant, does not depend on time and space, then you say that the fluid is uniform. So please remember, rho constant, that doesn't mean that the rho dt is 0. Of course it is 0, but it's not the same thing. If rho is constant is 54, that means that the fluid is uniform. But to say that the rho dt is 0, it means that if rho changes in time, this change is compensated by an opposite change in space. Okay? If we are in this case, it's equivalent to say that we deal with divergence-less conditions for the velocity field. Now, this is a case in many, many instances. Don't think of fluid mechanics as, as a 19th century science. If you go in context of cosmology, this is perfectly fine. And you may say, I know what you're thinking because it's what I was thinking when I was your age. I say, wait a minute, rho may changes. Yeah, of course. In cosmology, rho may changes. Ah, yes, but it depends on the scale you consider it. On the very large scale, you may assume that this is not rho, is not going to change, basically. And so you assume this case, divergence-less condition. Divergence-less condition. Okay, so this is conservation of mass. Now, I'm skipping, because I said you multiply by a unit vector, blah, blah, blah. So I'm skipping all that, and I just give you the dynamical equivalent of the kinematic transport theorem. So this is the transport of dynamical property. Now you take this G. G is now a vector or a tensor, right? And for this G, as I said, I skip the proof, which is elementary. You will have it in the notes. And you can prove the following. d dt of the integral on the volume V of this G vector in d3x. I use here an arrow instead of underlying, just for fun. This is, you go inside with the derivative, because there is some algebra to do. You go inside with the total derivative, and then you get this equation. So this is over V, and this is in d3x. Okay. Transport of dynamical property is easy to see that you get to there from the scalar quantity. It's not so difficult. Again, you have to do some algebra here. Okay. Now, which property? Well, for example, a momentum. So what about momentum? G is, you define it as some sensible quantity, mass per unit volume times the velocity, okay, rho u. And you apply that equation. So if you apply this equation to this, you get to the conservation of linear momentum. Okay, so I'll do it in a moment, but first I want to show you something. So we have a lemma here, a little lemma that is the following. Let G be this rho u. Then we have the following. We have the d dt of the integral over V of rho u in d3x is equal to the integral of rho du dt in d3x. And to prove this, I will do a little proof here. By doing this, since we attribute to G a fluid mechanical meaning, G is now the product of the fluid dynamical density times the fluid dynamical velocity, U, then we can use the conservation of law for mass. So we have to use that conservation law here in order to see that from here we get to this. Okay? So this is also pretty standard in textbooks. Is not a big deal. So you do the following. Okay, a little proof of this is d dt of this quantity rho u d3x. This is the integral over v of d rho u dt, plus we apply the kinematic transport and in the version for vector quantities. So it becomes a dynamical transport theorem, divergence of u in d3x. Okay, and now what we have? Now d dt of rho u plus rho u of this quantity, divergence of u, is rho d u dt plus u that multiplies d rho dt plus u dot grad rho plus rho u dvu. Okay, so here we are with rho du dt plus u that multiplies d rho dt, and then we work out this into this quantity, the divergence of rho u. Okay. And as you recognize, d rho dt plus the divergence of rho u, I probably deleted, it was a quantity that is due to mass conservation is 0. Okay, so we get to the result. Okay, I'm sorry, I just deleted that. Okay, so we are now ready to prove conservation of linear momentum. Okay, conservation of linear momentum is, so we start from what we just found, d dt of rho u d3x is equal to the integral of rho du dt d3x. So this is a momentum. We have to balance this momentum. You know, the system is subject to a momentum. This is not a balance equation. All right? This is just a way to transform this into that. Okay? We are just saying that the variation in time of the momentum has to be balanced by some forces. So this is not the balance of momentum. This is just a mathematical rewriting of this into this form by using a piece of math. Now we are just saying that this is a force. This is moving, rho u, a force, has to be balanced with a force. Has to be balanced with a force. This is the second law of Newton. So we apply Newton's law here. We apply Newton's law saying that this mass times acceleration, so to speak, is equal to a force. So we have to say something here. There is a force here. Now, here comes a point where I lose some friends and I acquire some others. I'm already losing a friend in front here because I'm now going to say that the forces I'm considering, there are two types of forces. One, why in books don't say this clearly? It's so easy to remember. Two types of forces. A volume force. You have a volume, imagine a sphere. And you have a force, imagine a sphere. It's not exactly like this. It's just a way to remember it. Imagine you have a sphere, and this is your elementary volume. And then you may say, okay, I have a force that is acting along the surface of the sphere, and I have a force that is acting orthogonally. Okay? Orthogonally. Now, what I'm going to say, I'm losing a friend here because I'm saying that I will neglect these kind of tangential forces. Well, I know, I'm going to lose some friends because I care. I care about these forces. Huh? I do care. But it depends on the context. It depends on the context. In the bulk of some cosmological space, these tangential forces are not so important. It depends on the context. And maybe these pressure forces are important. You know, you go to a Big Bang, and the Big Bang is an explosion, and what matters is the pressure you receive. It doesn't matter really if you're squeezed aside. You don't care about that, but the pressure you receive is enormous. So you neglect the tangential forces. They are there. They are very important, but it depends on the context. So let's say that for what I'm carrying in this course, I will neglect these stress forces, shear. I will have no shear, no tangential forces, no tangential forces, and I will take care of the pressure forces. Pressure forces. So I will take care of these pressure forces. All right. So let's keep some details because otherwise I'm not going too far. And if I'm doing this assumption, then basically I'm going to say that the forces I care about are of two types. One type is a pressure force, a standard pressure force. So let me call it, I can always, any force, I can write it as a volume force. And I can write rho little f for this capital F per unit volume and per unit density, d3x. This is one type of force I can consider. And the other type of force I'm considering is, so of course I have to express this force as a force on a surface, right? On a surface. So I will transform this into an integral over the surface where the force acts. So let's say a pressure, P, and the pressure P, I didn't put a sign here, but just I'm making up this. I will denote this with the perp sign, just to remember that these pressure forces are just orthogonal, no tangential component. So these pressure forces, I will call them minus little p, our pressure, and then I have a nu, which is normal to the surface S, and d2 dx over S. So I have to say, you know, I had a question mark here. I had to put in what forces I'm considering. Then there are other forces that I am happy to consider, and for mathematical reasons even more happy, because like this one, I can think of a potential instead of the force. So similarly, I can consider forces that can be derived from a potential. Potential forces. Forces that can be derived from a potential, we immediately think of one that everybody experience, gravity. So I write a force, but I now like to start thinking that I'm caring about the potential. Okay? 50 years ago, many physicists were abandoning the lecture room because if you were talking about potentials, nobody would have trusted you, because physicists like to do experiments and they don't see potentials. They see the result of the potential, right? We measure gravity. We do not measure the potential associated with gravity. It's potential, you know, from Latin. Impotens is in the theory of. It's not acting, but it's potentially acting. You know, the ball up here doesn't move, but if you move it away from the table, falls. So there is some potential energy that can be put at your disposal. But then came an experiment. In the, much recent actually, but was thought in the 50s by Aronov and Bohm, that show that potentials are important for physics. And gradually people started to think, even theoretical physicists, started to give more importance to potentials. Anyway, this is derouting. So I take care of forces that can be derived from a potential. Gravity is one, but there is another one, Lorentz force, associated with magnetic field. You know, magnetic field can be expressed through a vector potential. A field through a vector potential. And in actual fact, almost all we want can be derived from a potential. And this is helpful. This is helpful in the mathematics. So, okay, I have to put something here. And what I will do there is the following. I have this, and I can convert the surface to the volume as usual. So I will put all my forces there, and I will put, you know, there is in going from the surface to the volume, there is again a divergence theorem to apply. So I will write this as a grad P plus rho f, this little f associated with a force that has a potential, and this is d3x. So now this is conservation. I'm saying that the motion due to an acceleration is compensated by a force. There is a minus sign here, okay? Because if the pressure works in this direction, if it works in this direction, I have a minus entering. If it works oppositely, it's compensating. Think of, very easy, think of difference in pressure when you open a window. You open a window, immediately you feel some flow of air. You like fresh air. Why? Because there is pressure outside that maybe is much lower. And so the difference in pressure pushes the flow of air going out, or the other way around, or the fresh air coming in the room. Okay? So the pressure is the only force you consider, in this case, and then this little f stands for all the other forces that can be expressed through a potential. So instead of rho f, I can skip all this, and if you like, I can put some grad phi. Okay? Phi is just a potential, associated with gravity, associated with vector fields, whatever, it doesn't matter. As long as I have a grad of a potential, I can think of this as a contribution of grad of a potential. Okay, so I quickly get to a conservation law for linear momentum. that is this. And this law, we again assume that is valid whatever happens in scale. So we go down in scale, small scales. This law is equally valid for infinitesimal volumes. So from this law, we get to infinitesimal differential form. So conservation law in differential form gives, okay, conservation of linear momentum in differential form gives the equivalent rho du dt equal minus grad p, and then we can put gravity or some other forces. If I stop here, well, this is a pretty famous equation. This is exactly Euler equations. This is Euler's equation. So Euler's equation comes from conservation of linear momentum, application of Newton's second law, and neglecting the presence of other forces. It's fine. Well, it depends on the context. You may say gravity is not so important after all. It depends on the context. And so you may say that this is the equation. You are not happy, you want to include all forces that are coming from a potential. Okay, you can put it like so. Okay? So this is the equation without dissipation, without shear stresses. Now, I use the rho, so I keep rho there, rho f. Now, I want to do it, or I may, with the choke I can do what I want, it's not a big deal. I can put forces acting on tangential directions of the volume, so I have to add an extra force here. And this extra force, I will do it now, but I won't use it, this equation. But it's so important that I cannot escape just to mention it, that through some consideration about the action of these tangential forces on an elementary volume, again, we think of big equations, but the origin of concepts are simple very often. We should focus on concepts. Concepts is, okay, we go at the time of Hooke's law, and Hooke relates the changes, as we go down against the surface, it emerges a friction, because we are going from one state of matter to another. And when we change state of matters, very often we feel this friction. And this friction is what we call now viscosity. Viscosity. And we have to take care of viscosity, very often nu, or there is a mu, dynamic or kinematic viscosity. And then there is something here that is an operator that is two derivatives of the velocity. This is an operator that includes two derivatives. So these are no longer Euler, are more general, and are Navier-Stokes. Navier-Stokes equations. Navier was an engineer, French engineer. He worked on elasticity. And Stokes, of course, was a great applied mathematician. And they derived these equations. And these equations, of course, was a big trouble to derive this term. And in 1858 came out a very famous paper. I will focus on that in particular, a paper by Helmholtz on vortices, vortex dynamics. And it's very interesting to read the front page of this paper, because he confronted the community, the scientific community of the time, with two problems. He said, I want to tackle one of these two problems. They are considered equally difficult. One is what is vortex motion? We will introduce the concept of vorticity, the concept of rotation, and as you can imagine, without knowing really technically what we mean, you imagine that if you steer some fluid, there is a rotation. You may construct an operator that you know what is the curl. But what happens at the center of this curl, exactly point-wise? Velocity goes to infinity? Of course not. Nothing goes to infinity, right? But the community disputed, because the idea of a vortex was okay, but the idea that at the central point of this vortex, the velocity couldn't be defined in terms of finite contribution was a puzzle. Velocity had to go to infinity, because you go, metrically speaking, to 0 dimension. So the curl is what we could say now a delta function, right? In ideal. And the other problem that nobody wanted to tackle is this one, the role of viscosity, how viscosity was playing in this equation. So he said just simply, okay, I want a duel with the viscosity because Mr. Stokes is working on that already, and probably some progress are in light. I want to tackle the problem of vorticity. So I will follow this approach. I will not consider viscosity in this talk, however, in this course of lectures, but of course viscosity is important because in many, many cases viscosity not only dissipates, well, we know that, but it dissipates topology. Is viscosity that creates changes in topology. So we have reconnection of structures. Structure meet, vortex filament approach each other, vortices approach each other, and immediately mix up. So it's viscosity. Because if there is no viscosity, if we are in an ideal situation, something else happens. And I want to focus on this because it's so interesting also for theoretical physics point of view. So I will stick with this problem, the problem of Euler equations. Okay, so these are just conservation laws for the linear momentum. And now I want to introduce you very quickly, as I did for this first part, to another very important concept. So, concepts have history now, and we have to go back to history to learn a little bit, and so I'll be very quick. But at a certain point, we are again at the time of Lagrange, at the origin of, we use Taylor expansions, right? And so we are thinking, we have a function, we have to expand. And so the idea of Lagrange is, okay, I'm on my boat, which is a molecule, and I want to find out the motion around me. And I want to study this motion. So I have to resort to a very classical example. Before doing that, let me introduce, because I mentioned it, vorticity. So I define vorticity. You remember, we had a streamline. A streamline was a line in space, C, R3. And on this line, I said that at each point there is a tangent, and I identify the tangent to the curve, which is just the geometry, with a velocity field. And I call this velocity field U, or whatever I called it, right? And we had the definition, if you remember. We had the dx over u equal dy over v, the three components of the velocity, dz over w. I can do this for any field line. I identify the components of the tangent, dx, ds, okay, dz, ds, etc. S is just arc length here. I just identify the components of the tangent with the components of the field. So if I introduce a new field, vorticity, I do the same, vorticity. Vorticity is just omega, and this omega, I think of omega 1, omega 2, omega 3, the three components, and then I define this field as the curl of U. Okay? The curl of U. This is the problem Helmholtz had. The problem is that Euler, everybody knew, Leonardo, we go back, everybody knew that if you steer it rotationally, a fluid, you have rotation. But what happens at the center of rotation? It looks like the velocity goes to infinity. Think of the structure of rho. Is derivatives, combination of derivatives with respect to space. But if you go space to 0, then you have some trouble. Okay, so for those of you who don't remember, I don't remember, dw over dy minus dv over dz. Then we have the other component, du dz minus dw. The way I write it is certainly the way I don't remember. I have another way to remember, but if I want to explicit it down, I have to think. dx minus du dy. Okay? This is the curl. The curl in R3, of course. The curl in R3. Can you have a curl in R2, in R4? Think of string theory. String theory, how many dimensions you care about? Even or number, or odd? A curl in R2 is what we teach to undergraduates, is a vector that comes out of R2, is not in R2. Suppose you are in R2. Can you see the curl? No. The curl is out of R2. You need R3 to see R2. So if you want a vortex in higher dimensions, 11, you need an odd number of dimensions to give full meaning to the curl. Okay. So we have vorticity. Of course, you give meaning to a curl in R2. The way I said it is out of the plane, normal to the plane, blah, blah, blah. But it's out of the plane. If you belong to that plane, you cannot see it. Okay, so you have a curl now, and I'm skipping a number of details just because I don't have time enough. And I will say that we have a decomposition of motion. I will turn this decomposition of motion into a decomposition of fluid motion. I will give some physical meaning to this. But let me start for a moment considering just purely kinematics. I have a point P, and I move this point a little bit by a vector little h to a new point Q. And I want to relate the motion, eventually of a fluid, of this point with respect to this. So I say that suppose that this coordinate is x, and this coordinate is y. So I say that the velocity u at y, where y is equal to x plus a little h, that stands for a little perturbation from this position, then this is given by u of x. We are doing nothing else than again Taylor expansion. I'm here, I want to say something here, so I say something here in terms of what I have here plus the displacement. Okay? Simple concepts. Very, very simple. Then you work out the little mathematics, it becomes a little bit more complicated, but the concepts are so simple. Okay, so you have u of x, but I want to know u of y. So u of x plus something. Here you have to have a kind of Taylor expansion. So allow me to write this as a matrix. I won't tell you much about this matrix because I don't have time. It's written here and is a standard information. This matrix is like a tensor. I just double underline it. And this is times h Plus, I still have terms in H, and I will drop terms in H squared, consistently with Taylor expansions. So I still have terms in H. So I say, okay, plus a half of omega, first derivatives, of x, of course. There is no time for the moment. Cross product, maybe I use a wedge operator, wedge, H. Plus, and finally I drop these terms. Order of magnitude H squared. Okay? So this is Lagrange. This is Lagrange. We can say Lagrange. So it's an old observation. And as I said, derives from expanding near a point, a given function. And then I'm just quickly moving away from that, because I want to talk about physics. So I want to give physical meaning to these terms. And again, you will find a proper discussion in the notes, but let me say just quickly that from there, I go to decomposition of fluid motion. So I attach a physical meaning to that, and I have that the fluid moves at y in terms of three contributions. I neglect that one, so let me do this. Approximately given by a u of x, and this u of x is just pure translation. Okay? Let me use the notation I used in the notes. Okay, so this is pure translation. Then I have a contribution due to this d. What is this d? Oh, this d is, so first of all, is a kind of tensor, is a matrix, 3 by 3, and it tells you that the volume gets deformed, and is related to that, to the divergence of u. In appropriate coordinate systems, that matrix can be reduced to the diagonal form, and the sum of the diagonal terms gives you dvu. So if you sum up the diagonal terms, you have dvu. Here I state dvu equals 0 is a particular case. So you may have this deformation matrix that is exactly the determinant 0, but not necessarily. I didn't assume incompressibility yet. Incompressibility means solenoidal fields. Divergence 0. For the moment, in general terms, I have this deformation tensor that gives me some deformation, so I will call it a UD. A UD means that the fluid, the volume deforms. It may stay constant in volume, or not, it will deform. Okay, so this is UD, and plus I have an UR. Okay, so sorry, everything at x, or close to. So rigid translation, deformation or distortion, let's say volume deformation, and this is rigid rotation of the volume. Okay, I've been very quick here because what I want to focus in not only in this decomposition, well, this is okay, but I want to start from this decomposition. I want to start from here now. I want to analyze these terms because I want to say that the fluid moves because of the combination of these terms. Some are important, some not. For example, I may have no rotation at all. If I have no rotation, my fluid will translate and will deform without rotation. I may have no translation at all. and so on. So let's analyze case by case each of them. So by analyzing each contribution, we provide an expression for the velocity, and this expression for the velocity adds up with the other expression for the velocity and so on. We can combine these expressions into one, and this finally the u of y. Okay? But I do this not only as an exercise, but this is useful because we meet some problems. We meet some interesting problems. We face interesting challenges. For example, the first case. First case, you know, I'm going to have three cases. I have three components there. So I'm going to neglect the other and focusing on one at a time. So first case is when UD is equal UR and is equal to 0. Okay? So I'm just rigid translations. So, okay, so I will have div ut equal to 0. And sorry, I'm just wondering if I made a mistake in what I wrote. Okay, yeah. No rotation equal to 0. This is related to assuming UD equal to 0. Believe me, you have to read. And this is given by assuming UR equal to 0. There is no rotation, so the contribution from UT, by definition, are 0 in terms of rotation. Because what I have from rotation would go into UR. And what I have from deformation would go into UD. So clearly, div ut is 0, and curl of ut is 0. This, how old we are there? We are little kids in science, because we are at the time of Laplace. He was, I'm now, of course I'm joking, but in a sense, he was a cosmologist. He wanted to study an equation for the universe. One of the very first beautiful pictures or drawings of a universe from Laplace when he was coupling, so to speak, these two equations together. Because you know where we're going. We're going to the Laplace equation. We're going to the Laplace equation. So since there is no rotations, since there is no rotation, then we can use immediately Stokes. We use the Stokes theorem, and we have the curl of ut nu d2x over some surface, and this is exactly the integral along the boundary of this surface of ut dl. And this is 0 because there is no rotation. And I use the C as the boundary of S. Okay, there is no rotation. I use Stokes. This is 0, so evidently this is 0. And this is the starting point of what we do in Physics 1, maybe, I don't know, Physics 1, first year of physics, when you introduce this, and then this is a closed curve, and then I skip some details because I have no time, but you understand what I'm aiming at. I'm aiming at the fact that the circulation of ut along a closed circuit being 0, it means that I can define a potential. I can define a potential. Now, how I choose C? Oh, any C. So this C this C, or any other C, doesn't matter. Whatever C I choose, this is 0. Now, you do a step. A step is this. In mind, you know that this is 0, okay? Now, you forget about this. Forget about this. You know y is 0. And you read this as if you didn't read anything else. Somebody tells you that this is 0. And somebody tells you that ut is different from 0. So there are two ways to think about it. One is to have C 0, shrinking C to a point, continuously. No obstacle, no obstacle. You can continuously shrink it to 0. The other is to prove that you can continuously shrink to 0 by working out ut in dl, by working it out. Okay, so you can subdivide this circuit into a C1 and a C2, C being C1 union C2. And then you want to start here and end up there along these two paths. So suppose you cut C1 in this part and C2 in the other, so you have to reverse orientation, okay? You have to reverse orientation. So if I reverse orientation, I can start from here, getting to there, and then I want to start from here and getting to there, just by taking the arc length with a minus in front of it. If I took the arc length with a minus in front of it, I would do this. And clearly is 0. Because this path and this path is 0. No matter how I rewrite it. Okay, so let me show you. It's just very simple. Is this the integral of ut? This is just physics 1, dl along C. And we know that this is 0. And this can be split in C1 ut dl. dl is now the arc length along the curve. C1 plus I take the other one. For the moment, I keep for the first part of my passages, I keep the length the same. So orientation is going all the way consistently. So I have a C2 ut dl because I simply split the integral. But now I want to reverse sign. I want to go here to here along the direction, and I'm just reversing sign. So the second curve will change sign. I have ut dl minus integral C2 ut dl. Okay? I can say that, this minus, there is an inconsistency in what I wrote. I should write something like this. Let me find an escape route. Escape route is, I call this L bar, this orientation, and then this L, the other one. So minus L is L bar, or the other way around. Okay, so I'm here. We know that this is 0. So we know that this is equal to that one. Okay? And now you do the discovery. Now you find that the value of ut is what they say independent from the path. No matter, this is not 0. I stop here. But this value here can be reached by any path I want. And any closed path, ut being different from 0, means that can be reduced to 0, because the value is 0. ut is different from 0. It means that the path can be reduced to a point. This is important for topology. Okay, so if we do this in what they do in textbooks, is to find the potential. It means that any CI, any path UTDL will give you, can be written as a difference between two values, and this is the potential. The difference between a potential, so let me say from O to P, UTDL, whatever is the path in between, it depends only on the beginning and the end. Okay, I show you that it's independent from the path. So I can choose a function phi at P minus a phi at O. And then I do what? I shrink again in size, so to speak. I go to elementary aspect. An element of this is just a differential, and the differential is just not a difference, but a differential. So I get to the gradient, okay? So I can define a gradient. From here, I can say that UT can be written as a gradient of a function, grad phi. Let me put a T, okay? So grad phi, phi being the kinematic potential for the velocity u. Now, I do all this. It's fine, but let's focus. Let's just point out one thing. So everything is okay. It's done in books, etc., etc. But in some books, they point out, well, suppose I do this. I do this as an engineer. You know, I think of a river where one day Lagrange would go on the boat, but the river has a pillar, and in my case, I want to choose a pillar in the water. So I have a pillar here, made of concrete, with a flow around it, right? Like this, and then, of course, it cannot hit there. It goes like this, and a nearby line would go like this, etc., etc., etc. And I'm back to the idea of this circle C and the circulation of UT dl being 0. I'm back to this idea. And I said, okay, this is 0, so I can pick up any C I want. But you're clever guys. You're a clever guy. You know, there's a pillar there. Come on, everybody knows. There is some vorticity. There is some rotation there. Maybe the fluid is rotating, or in front or backward, as a boat. As a Lagrangian boat. Suppose we don't think about that. Suppose we don't think. We say just UT is present, and not you are, and not you are, and not UD. Then I can pick any circuit I want. Okay, I take this circuit here, and this is C, and I construct my integration, and I can, because UT is different from 0, I can go down with C. It's the only way to make sense of this statement. So I can go to a point where I cannot continue. There is a solid there that prevents me to go down to 0. I'm contradicting this. Something wrong. So the only way to come up with this is, with a solution, is to say that UT is satisfying this relation only in one case, when I have no pillars in the fluid. If I have a pillar in the fluid, I need some other velocity, because this is not enough. There is an inconsistency if I assume that there is only this velocity field. Either I have a different contribution from U, we know which one, UR, rotation, or we say, okay, I don't have anything else. In that case, I cannot have a pillar. Now, I invite you to think of this, not of a pillar, but of an empty region, the complement of what you say. This is a hole. This is a hole. This is a hole, and this is full of material, fluid everywhere. and this is a hole. And suppose this hole is made so that no fluid can go inside or outside, because UD is 0. That means that my ambient space is no longer simply connected. So for this to work, I need ambient domain being simply connected. What does it mean, simply connected? It means that any curve I draw on this domain can be reduced to a point, is reducible. If I have a hole or two holes, even worse. It's very interesting because I have no time to go into this, but I like to tell you anyway, because it's good to say it loudly, that Kelvin considered this problem at his time. And why I want to emphasize on that? I want to emphasize on that because if this hole is a black hole, then we have problems in defining the potential in the universe. We have to amend, to correct some theorems, in particular Green's theorems, for a multiply connected domain. So there is some work for you guys to do. And this is what Kelvin started to do. And he started in the most simplest way. How? Well, think, always good start to think simple. It's easy to start thinking complicated, and it's very hard sometimes to imagine the simplest case, but this is interesting. So he thought, okay, I'm putting like a patch, I'm gluing a patch made of the same, so to speak, material, and I'm connecting the space. So I take some theorem with holes, not in the theorem, but in the domain, and I fill the holes with a patch, and this patch has to be an integral of a surface, so I have to add integral on the surface, and this surface is the surface of the patch I put in. And how many? Well, if I have one hole, I patch one piece of hole, one piece of fluid. If I have two holes, I have to do it twice. So I have integral on a surface plus integral on another surface, because maybe I have another hole here. Two holes is different from one, right? Unless they touch and they merge. We have this problem. Cavity, cavitation, bubbles in a fluid. Bubbles in a fluid. Bubble is air inside the fluid, and there is surface tension that keeps this air confined, and only when the two bubbles touch immediately became one, because the surface tension is a curvature force that makes the two bubbles gluing together. It resembles a little bit remotely, quantum tunneling somehow. Physics is not so different from one topic to another. It depends how do you see it. So, if this happens, of course, you reduce complexity, connectivity of the domain. You reduce connectivity from two holes to one hole. And then you like to have maybe this working, so you have to understand how to patch one hole only. This is exactly what Kelvin did much later. When you have to read this is interesting, you discover that one of the best review of all these ideas, you know who wrote it? I bet you don't know. Is written, I would probably say that one of the best introductions to topology is Maxwell. Maxwell. You're thinking electricity or magnetism, right? The two volumes. And I know what you're thinking. You're thinking, there is no topology there. I never saw topology there. Well, first of all, piece of advice, when you go at that time, don't check for topology, because the term topology was introduced by Listing later than Maxwell. or more or less the same time of Maxwell, but it's not in Maxwell's book. You have to read or look for geometry of position. And if you look for geometry of position, you find something amazing, that Maxwell discusses a whole chapter on that. Did you skip it? I think, yes, you skip it. Why you skip it? I tell you why. Because it's called preface. Preface is chapter 0. It's chapter that does not exist. The chapter that does not exist, i.e. the preface, in Maxwell Volume 1 of any edition, is entirely devoted to these aspects. Maxwell understood immediately the importance of topological connectedness in terms of potential. If potential are well-defined everywhere or not, and we know now, after Riemann, that these are not well-defined. If the ambient space is multiply connected with holes, the potential has multi-value. That's why for black holes, for universe full of black holes, we have a problem. So complain to your high energy or other astrophysicists or cosmologists to tell them, look, we have a problem here. The potential is not uniquely defined everywhere. If we have black holes, we have to amend the theory. So Maxwell introduction, preface, you go home and you check. And you start reading. And after a while, you recognize immediately what I'm saying. Because he talks about multi-connectivity of the ambient space and the potentials that have multi-values are not uniquely defined. And this is also central topic in one of the 11 papers of Riemann. Riemann starts exactly from there. So I will go on because I have to finish with this. So this, I emphasize this. Of course, we came from this equation, we ended up with this equation, and now we substitute u here, and we take the div of the grad, and we find Laplace. Okay? We take this, we combine this with that, and we get Laplace. Laplace. Okay? Laplace equation. Let me dwell a little bit on mathematics. Laplace equation, you taught that solutions to Laplace equations are called harmonic functions, right? So if you look for harmonic functions, you have to look for a domain where there are no pillars. If you have a pillar, then the function is not harmonic anymore. So this is known, but it's not so. You know, it's one thing, I know where he lives, and the other is going to ring the bell. You know, I know where he lives, and then you go there and you say, yeah, I know where he lives, but I don't remember exactly. And this is the same thing. It's the same thing. So it's known, but any effort to understand better that? I don't think so. So we are now at the time where this is another issue. I mentioned singularity issues, I mentioned the role of viscosity, I mentioned the role, lots of issues. This is another issue. Where is important? I'm facing this as a research topic nowadays, so I'm happy to communicate this to you. I'm facing this in defects, Bose-Einstein condensates. Bose-Einstein condensates are defects, they are pillars. It's not simply connected, the domain. If you have a defect, you have a multiply connected domain because you have a pillar, the defect, in the cross-section. And if you have this defect, then harmonic functions are not well defined. And there may be several degrees of, let me coin the new word, of non-harmonicity. You may have several degrees of that because you may have different holes, more than one, 2 or 3, you know. Remember the air bubbles. They can merge, and you reduce complexity. So you can have defects that merge, and you can reduce complexity, and you go towards harmonic functions. But you are not quite there because defects are there. If the defects survive in your physical experiment, then you are not dealing with harmonic functions at all. You are dealing with functions that are intersecting. Functions that are intersecting. Surfaces that are intersecting. They are not smooth everywhere in the whole domain. Somewhere they intersect. Where they intersect, you have a new defect. You have a singularity. A physical singularity. If we keep this example of Bose-Einstein condensates, you know, there are physical singularities. They are not mathematical singularities. Because physically, you go to a point or to a space, to a line where surfaces, isophase surfaces intersect. This line is a line where density is exactly 0. Or vortices in superfluid helium, again, a state where you go to nano angstroms, and there you have a hole. You have a hole. You have a vortex. But the vortex is confined on a surface. Inside the vortex, there is a hole. There is a hole. They send electrons to visualize these tubes. All right, so we are there. So if we are there we have to work on this, and this is big work, okay? You know, books on harmonic functions, and how to calculate these harmonic functions, whatever is the geometry, blah, because you may have different geometries. Boundary conditions, I didn't mention boundary conditions. Of course, you have boundary conditions. I'm assuming an infinite domain, but if you have boundary conditions, you have to deal with that. And boundary conditions are of 2 types. I'm just quickly reminding you, a Neumann condition. I'm again stimulating your fantasy. You have to remember these things. I cannot remember names and algebra. So I associate Neumann and normal. Normal to the boundary. Okay, this is the way to put. So the normal to the boundary, it means that the fluid is going through the boundary or not. If it is not going through the boundary, you have a normal condition to the boundary to prescribe. Velocity 0 equals 0 at the boundary. Or Dirichlet condition, this is the other one, okay? So you have boundary condition, and you can solve that, you find harmonic functions. I want to move to the other case, is the case where we have some deformation, UD. Sorry, I do this. So we said UD 0, UR 0. We are second case now. Second case. In this case, we put UT equals 0 and UR equals 0. And then what we have? We have div UD different from 0. We have divergence. We have divergence of this field. Divergence of this field, well, I can use a letter, say eta. Something. Oh, you know this. You know this. You know much better than me this. And I now push you in another direction, very far from fluids, and not so far. Electrons. Yeah, electrons. Is an electron here, so there is a charge. Right? That's it. That's it. So it is divergent. Something is divergent. In fluids, okay, if you want really to talk about fluids, okay, it's not an electron, it can be a sink or a source. It's the same thing. It's a field that comes out from something or it goes into something. So this is different from 0. We assume eta is different from 0. And what we do, and the other one, we have no rotation. So clearly this UD is not rotating, is not contributing to rotation, otherwise we contradict our assumption. And then in this case, well, we quickly get to this equation, but now it's not 0 anymore. It's not 0, it's eta. This has a name, and sometimes mathematicians don't recognize this with a name. I like to use a name. I call it Poisson's equation for something, for eta, because I want to be specific, because this equation will come up in a moment again. So I will say Poisson equation for something, for eta, for expansion or contraction due to eta. Okay? Now, this was tackled by many people, and it has a solution. And I will skip this solution. It's important. I want to get to that's right. I want to get to the other case because the solution is identical, is formally identical. So let me pause for a minute. I have that equation, okay? I will come back to that equation, but just let me go. And so let me go on, and I say, okay, we have a solution for that equation. And bear with me. So the solution will be UD equals something. I'm going to say it in a minute. And then I move quickly to the third case. Sorry, I will pick up all the chalk in a minute. Okay. Third case. Where I am, here. Third case is gone. Well, I can come up without reading. Okay. And the third case is where UR is not divergent, and the curl of UR, oh yes, now we have the curl of UR, which is vorticity, by definition. So here we have a little bit of all these bad vector identities to use. I'm skipping this. You will read it. But you know, we have to have, from here, we have omega equal what I wrote. So what I wrote is curl of U. And now U is a vector. I want to go to the potentials. So if I want to go to the potential, I define this vector in terms of another vector, the curl of A associated with this UR. I can always do this. This is the vector potential associated with U, and you are again at home, because think of the magnetic field, and this is exactly the vector associated with the magnetic field. But I have to solve this equation, so I have to do some vector identity, vector algebra, calculations, and this gets you to another Poisson equation. The Poisson equation for another field, for A. And this Poisson equation is a bit more general than that because eta is a scalar. But now I deal with omega, that is a vector. That's why I didn't want to spend time on that one, because that one is kind of simpler than the one I want to talk about. And the one I want to talk about is this, is minus omega. So this is, of course, Poisson equation for vorticity. In doing the algebra in between, I made an assumption that if you were totally, 100% in fluid mechanics, probably I would have said, I wouldn't have said that, but because some of you are interested in many aspects of physics, I will like to remark that here we assume a Coulomb potential. We assume Coulomb potential. We assume Coulomb potential. Okay? That is the cage potential. Yeah. Cage condition. Yeah. Okay. Okay. So we get to this equation, and if you look at each component for vorticity, each component, omega 1, omega 2, omega 3, you can think of each term as that one, basically. But we want to find out UR. Remember, UR is our aim. So we want to solve this equation, or that equation. We want to find A in 3 components. And once we get A, it's somehow easier because we have just to derive A in order to get U. This is easy. It looks awful, but it's easy. You do derivatives. You know, you remember high school or first year undergrad? Oh, integration. There is no general theory of integration. So it's a pain in the neck. Derivatives, easy. Integration, according to the case, you have to apply a certain rule, they were saying, you know, by parts or by whatever, change of variables. When I was 18, I had a very good friend of mine who might have been now, he might be a very famous mathematician. I apologize because I don't remember his name anymore, and so many years passed, we lost contact. But he was very determined to study mathematics because he said, I want a general theory of integration and of partial derivatives. That was a very good aim. I want to find a technique to reduce partial derivation to ordinary derivation, find these directions, and so integration will be the outcome. It will be easy, a general rule to integrate whatever is the function. I still teach a little bit of integrals to first-year students sometimes, and as long as I know it's still there to be solved, the problem. But so you know, once you have AR, it's easy, let's say, because you do derivatives. Derivatives is easy. But we have to get AR. AR, we have to undo this operation. We have to integrate in order to have AR. And the integral has a name. I skip passages because I want to get to the U. And the U, as a result, we have a U, UR. And UR is a famous equation that you know very well in electrostatics. And this is the Biot-Savart equation. You have a minus 1 over 4 pi integral over, say, a volume. Let me call it a W for some reason. Omega. Let me call it X star for some reason. I come up in a minute. Here I have UR of X. And this is the situation. Wedge, X minus X star divided by what we recognize very well as the green function. 1 over X minus X star is the green function. And this equation, I'll stop here. Biot-Savart. Biot-Savart. Let me emphasize induction. Induction law. For vorticity. Of course, you have the same kind of information, simpler, because it's just a scalar quantity, for the expansion, for eta. Okay, it's the same. Formally, it's the same. Now, let me emphasize on this one, because this is terrible, as is terrible, that one. It's terrible because there are lots of features here. First, you already noticed one feature. The feature is that I'm putting stars. I have a pillar there, and now this pillar is the region of vorticity. Is a big tube of vorticity, a vortex tube. I'm taking the cross section, so you know all vorticity vectors are coming up like that, and it represents a obstacle for the fluid outside, because the fluid outside cannot shrink to a point anymore in presence of this vortex. And the regions here are denoted each point by x star, and the point here is x. I distinguish a point outside this region from a point inside this region, and I say that the velocity induced on this point, x, outside this region, is due to what? To an integration over the distribution of omega, which I should know exactly, which is already something, because I not only have difficulty to say something about omega, but I have also to add something that in books is not done very often, information on the domain where omega is. If everything is steady, static, does not depend on time, okay, maybe the domain does not change. I said that is an assumption. I assume that everything does not depend on time, so the domain is fixed. Still a big trouble, because this domain looks like a circle, looks like a disk. But what about if the domain is something very odd? It's normal in nature. We don't have exactly the geometry that we inherit from the Greeks. If it is steady, okay, and if the domain has a geometry that we can handle, it's a big if, okay, in that case the geometry is given, the vorticity is given, we can work out this integral analytically, not yet. Only in very, very, very specific situations. For example, when this pillar is infinitely long and straight. For example, when this cross-section is a cross-section of a perfect torus. Almost that. Two cases. The straight line, or the straight tube, and the torus. Okay, the helix, with some difficulties. And then that's it. If you prescribe omega, the volume of vorticity, to be, for example, a region that makes a knot in space, oh, forget about an analytical solution to this. And if everything changes in time, forget about an analytical solution of this. But this is so central. It's central because it gives you a U that all the times plays a role in the big U, in the U of the fluid. So in order to determine this, you do a lot of work on this, numerically. I will stop here, because we touched upon the role of topology in determining U, and this essence, the devilish structure of Biot-Savart law. Remember that the devilish structure is not finished in the fact that we don't know W, we don't know omega so well, because maybe changes in time, but when x goes to x star, we have a singularity. We have a singularity in velocity. It's exactly the type of singularity that Helmholtz faced when he started to work on vortex motion. Everybody, the mathematicians, were saying, nah, something is wrongly posed, because you're going to have a singularity when x is equal x star. And is a famous business in dealing with this singularity. Part of my PhD was on that too, because I worked on helicity and how to tackle this singularity that, once again, you learn from high-energy physics, to desingularize through techniques that are very elaborated. Okay, I'll stop here, and tomorrow we keep going. Thank you for your attention.